Star kinematics is a branch of astronomy that studies the motion of stars in space. This field explores the velocities of stars in the Milky Way and its satellites, as well as the internal kinematics of more distant galaxies. How do astronomers determine a star's membership in a specific kinematic group? What key characteristics of stellar motion allow stars to be grouped into a single kinematic category? A kinematic group of stars is a group of stars that share similar motion characteristics and age. Stars in such groups may have a common origin, such as being remnants of a dispersed star cluster, or the result of the merging of regions where star formation occurred at different times. As these stars age, they may leave their groups or cease to be gravitationally bound, leading to the formation of star associations. Star associations are loosely bound groups of stars with a common origin, but no longer gravitationally connected. They can be identified by their common motion vectors and age. These were first discovered by V.A. Ambartsoumian in 1947. Star associations are divided into several types, including OB associations, which contain massive stars of spectral types, O and B. They typically exist for only a few million years, as O-type stars explode as supernovae during this time. One well-known OB association is Scorpius Centaurus, which consists of several subgroups containing young massive stars and is relatively close to the Sun, about 400 light-years away. T associations include stars of the T Tauri type, which are in the process of transitioning to the main sequence and are often found near molecular clouds from which they formed. R associations are groups of stars that illuminate reflection nebulae. These stars are not massive enough to disperse the molecular clouds in which they formed, allowing astronomers to study the properties of these clouds. R associations are frequently used to study the structure of spiral arms in galaxies. When stars that remain from a star association continue to move together, they form a moving or kinematic group. These groups can be either old or young. For example, the HR 1614 group has existed for about 2 billion years, while the AB Pisces group is only about 120 million years old. Is it possible to determine how many galaxies have been absorbed by the Milky Way over its history based on stellar streams? A stellar stream is an association of stars that were once part of a globular cluster or a dwarf galaxy, torn apart by tidal forces and stretched along its orbit. One of the well-known stellar streams is the Arcturus stream, which includes the bright star Arcturus and many other stars with common characteristics, such as proper motion, indicating their physical connection. This stream lies outside the plane of our galaxy, the Milky Way, and is likely a remnant of an ancient dwarf galaxy that was absorbed by the Milky Way. The stars in the Arcturus stream are old and contain a small amount of heavy elements, which also indicates their ancient origin. The stream was first discovered in 1971, but it was only confirmed through research conducted at the Australian Astronomical Observatory under the leadership of Quentin Parker. Later, scientists such as Ivan Minchev from the University of Strasbourg suggested that the Arcturus stream formed as a result of the absorption of another galaxy by the Milky Way about 2 billion years ago. How does the movement of stars along spiral orbits affect the formation of planetary systems outside our solar system? For a long time, the task of detecting exoplanets remained unresolved because planets are extremely small and faint compared to stars, and stars are located at vast distances from the Sun. However, since the late 1980s, successful attempts to detect exoplanets have begun. Modern methods now allow us to detect these planets at the technological limits. The main exoplanet discoveries have been made using indirect detection methods such as measuring changes in the motion of stars rather than visual observations, which are extremely difficult. As of mid-November 2024, the existence of 7,352 exoplanets in 5,043 planetary systems has been reliably confirmed, with 1,022 systems containing more than one planet. Among the most promising candidates are the Kepler project, with about 2,000 candidates, and TESS, with over 4,600 potential exoplanets. To confirm their status, additional registration with ground-based telescopes is required. The total number of exoplanets in our Milky Way galaxy is estimated to be over 100 billion, of which 20 billion could be Earth-like. Furthermore, about 34% of Sun-like stars have planets in the habitable zone, which could be similar to Earth. In the search for Earth-like planets, scientists focus on exoplanets in the habitable zones, where liquid water might exist. There are various methods for detecting them. The most common is the Doppler method, which detects exoplanets affecting the motion of their stars. The transit method allows the detection of planets passing in front of their stars, reducing the star's brightness, which helps measure the planet's size and study its atmosphere. There is also the gravitational micro-lensing method, which can detect low-mass planets, while astrometry tracks changes in the star's movement caused by the planets. Additionally, there are projects aimed at more detailed studies of exoplanets, such as Pegasus, ECHO, and the Advanced Technology Large Aperture Space Telescope, ATLAST, which may aid in the search and study of exoplanets in the future. On the European Extremely Large Telescope, currently under construction, instruments will be installed to study the atmospheres of exoplanets, offering new opportunities for research. Scientists predict that there could be at least 300 million habitable planets in the Milky Way galaxy. Habitable planets are those where microorganisms, plants and animals could exist, although the presence of intelligent life is not a necessary condition. Forecasts show that if at least one planet with potential signs of life is discovered in the coming decades, it would confirm the existence of other similar worlds in our galaxy with a probability of 95 to 97%. What could the vast number of exoplanets be hiding from us, and how might they change our understanding of life in the universe? How does the Sun, a typical star of our galactic environment, influence the evolution of the Milky Way and the future of our solar system? The Sun is not just the center of our solar system, it belongs to the first type of stellar population, and its origin is shrouded in numerous mysteries and hypotheses. One of the most common theories suggests that the solar system could have formed as a result of supernova explosions. This assumption explains the presence of abnormally high amounts of gold and uranium in solar material, elements that could only have appeared through nuclear reactions triggered by such cataclysms. What could have caused this explosion? Is it possible that, in the future, we will uncover more about the origins of not only our Sun, but also other star systems? An important feature of the Sun is its ability to provide energy to the Earth. Solar radiation is the main source of life on our planet. This radiation is characterized by the so-called solar constant, which is 1.37 kilowatts per square meter at a distance of 1 astronomical unit from the Sun, that is, at Earth's orbit. However, as it passes through Earth's atmosphere, solar radiation loses a significant portion of its energy. On Earth's surface, under clear weather, and when the Sun is at zenith, only about 1000 Wm2 reaches the surface. This energy flow has limitless potential for utilization, from photosynthesis, which allows plants to supply us with oxygen, to converting energy into electricity using solar panels. Interestingly, the position of the Sun in the celestial sphere changes over time. Every year, its path across the sky resembles a figure 8, an analemma, stretched along the north-south axis. The most noticeable variation in the Sun's apparent position in the sky is its oscillation along the north-south direction with an amplitude of 47 degrees. This phenomenon occurs due to the tilt of the ecliptic plane to the celestial equator and influences the change of seasons. However, more interestingly, the Sun also alters its apparent size depending on where Earth is in its orbit at the time. By comparing the periods of aphelion and perihelion, one can notice that during winter, the northern hemisphere receives slightly more heat than the southern one. Additionally, the Sun is not just a star, but also a powerful source of magnetic phenomena. Its strong magnetic field fluctuates on an approximately 11-year cycle. These changes lead to solar activities such as sunspots and flares, which affect not only Earth but also its atmosphere, causing geomagnetic storms. This, in turn, impacts human health and the operation of technologies such as communication systems and electrical grids. But what are the other unexplored consequences of this magnetism? How might solar activity influence the future of our planet? Sunlight is not only a source of heat and energy, but also a crucial factor influencing biological processes. It regulates the circadian rhythms of many living beings, including humans. Recent studies show that light intensity exceeding 1000 lux can have a significant impact on human health. What happens when this light disappears? For example, in regions with little sunlight, such as the tundra, temperatures can drop to 35 degrees C, leading to a short growing season and low biodiversity. Solar radiation remains not only an object of scientific research, but also a subject of philosophical reflection. One of the first scientists to attempt to understand the nature of the sun was the Greek philosopher Anaxagoras. He argued that the sun was not the chariot of Helios, but a giant, hot metal sphere. Despite his death in prison for this heretical teaching, questions about the nature of the sun continue to intrigue humanity. Have you ever thought that in the future, we might unravel even more mysteries associated with this source of light and heat, which will remain unsolved for many generations? The history of solar observations spans thousands of years, from the earliest sketches of sunspots in China to the era of modern telescopes and satellites. All of this helps us expand our knowledge of the sun and its influence on our planet. How might habitable zones located far from the galactic center be the key to the search for life on other planets? Could such regions in the future become thriving hubs for civilizations in our galaxy?